In this last video of Module 4, I wanted to talk a little bit more about thinking submicroscopically about chemical reactions. In the last video, we talked about and looked at an example of analyzing the outcome of a reaction on the submicroscopic level, given a collection of molecules and a balanced chemical equation kind of serving as a recipe for how those molecules combine with one another. We can infer the outcome of the reaction, how many product molecules we get, and whether and how many of each type of reactant molecule is left behind. In this video, we're going to revisit this and then expand on this idea of generating a submicroscopic image of a chemical reaction in our minds. This is actually an important skill to develop the habit of getting into, because it helps with pattern recognition. You'll learn a variety of different reaction types throughout your study of chemistry, and each tends to be associated with similar types of change on the submicroscopic level. We're going to primarily focus on state of matter or phase in this video, and the submicroscopic images in our minds associated with those. But as you learn about more complex chemical change, you'll be thinking about the way atoms move, bonds are made and broken, and patterns in those on the submicroscopic level. We're going to start building that muscle in this video, and it's a muscle you'll continue to use and continue to build throughout your chemical education. So this slide we've seen before. This slide gets at the idea that if we're given a collection of molecules and a balanced chemical equation, a kind of recipe for how those molecules combine with each other to form products, we can infer the numbers and types of product molecules as well as any leftover reactant molecules that we might have left behind by applying the balanced chemical equation as many times as we can within the confines of the law of conservation of mass, right? We can't generate reactant molecules out of nowhere or perform a number of reaction events or reaction occurrences that is inconsistent with the numbers that we start with. So I won't go through the example again, but this kind of problem solving, thinking about a collection of molecules on the molecular level and seeing how many types of product molecules we get out, is a great way to get started with thinking about molecules and reactions on the submicroscopic or molecular level. The other place we can incorporate submicroscopic thinking is with respect to phase. So most chemical equations come with phase designators, or we can look up phase designators telling us about the state of matter of the reactants in the products. So for example, in this reaction, everything is gaseous, all four substances are gases, and so we can build on and use our submicroscopic model of what gases look like to visualize how this reaction occurs on the submicroscopic level. And so on this slide, I'm just reminding ourselves of the mental images we have for solids, tightly packed atoms or molecules, right, where things aren't really moving, liquids where there's a bit more motion, molecules or atoms can flow over each other, and then gases where there's very large separation between the particles and the substance will expand to fill the volume of its container and all that jazz. And then finally the aqueous state, where we think of the solute particles as separated, but not by empty space as in a gas, by solvent molecules that fill the space between those solute particles. Recognizing phase designators and triggering these mental images when we see the various phase designators will help us to visualize changes in the distributions of particles during chemical reactions and notice certain patterns. For example, just to give one example, precipitation reactions involve a conversion from an aqueous phase to a solid phase, and we can see that macroscopically as the solid crashes out of a liquid solution, but we can also think about that in terms of a molecular scale shift from solute particles that are strongly separated from each other to a nicely organized solid like we see right here. Here's a macroscopic example of thinking about visualizing chemical change using the reaction of zinc with HCl. So zinc is a solid. We actually see that from the chemical equation, right? We've got a solid phase designator right here. And the HCl is in aqueous solutions. This is mostly water with some HCl in there. We're also mixing in some HNO3, again, mostly water with some HNO3 solute in there. And here is our mixture of aqueous solutions of HCl and HNO3. It's a liquid, right, because it's mostly water with HCl and HNO3 solutes in there. And then when we combine things, check out the product side, we have aqueous ZnCl2, that's just going to look like a liquid. Aqueous ZnNO3, that's also just going to look like a liquid. But then we have 2H2, and you can see actually in this image that we're getting bubbles of hydrogen gas that are forming in the liquid and bubbling out of the solution. What the example on this slide shows us is that we can use phase designators in chemical equations not just to get an idea of the submicroscopic level, but also the macroscopic level. And this helps with pattern recognition and solidifying different reaction types in your mind, right? Many reactions of this type, metals reacting with strong acids, we should expect bubbling as a result of the formation of hydrogen gas, for example. Not necessarily a fact I'd expect you to know at this point, but one that we can start to recognize in the common phase designators that appear over here with H2 in a variety of different reactions, all falling within this type of single replacement reaction involving a metal and an acid. And you'll continue to kind of build this mental Rolodex, if you will, of different reaction classes and reaction types, and keep in mind that you can use phase designators for both a submicroscopic and macroscopic understanding of what's going on in the reaction. Here are a couple of lingering questions that we'll leave this module with. The first is simply, why do chemical reactions take place? We've talked a lot about chemical change in this module. We've written a few chemical equations. One thing we have not talked about is whether nature wants to do this or not. It's very clear when we actually mix the substances that this reaction in particular just goes. But something you'll learn in your introductory chemistry course is that if the reaction wants to run this way, then it does not want to run in the opposite direction. But why is that? Like, what is it about this collection of molecules versus this collection of molecules that makes this reaction want to run from left to right? This is something you'll explore in introductory units on thermochemistry and thermodynamics in your chemistry courses. The second question is really about mechanism. Most chemical reactions occur over two or more collisions between atoms or molecules. Many reactions are really built up of more than one reaction happening in sequence, in other words. How do we think about these reactions that happen in a sequence of multiple steps, and how do we study these? This is something you'll also touch on in more advanced discussions in your introductory chemistry courses.